morning. Let's continue on the lecture 246. Okay, I think last night the midterm went well. A lot of people finished really early. I guess I kind of underestimate or overestimate, I don't know, right? But anyway, so I'm happy that a lot of you finished early. But don't lose momentum. Make sure you keep working on it. I'll guarantee the final will be harder. Not because the question will be harder. Most probably because more material and then longer time, and you have many other courses at the same time. So when all this adds up, it becomes harder, right? So make sure you keep working on these things. So let's finish the first order differential equation today. Okay, so the last kind of first order differential equation we're going to cover today is called Bernoulli equation. And this is the last kind of first order differential equation. We have covered so far, if you recall, first order linear ODE. Okay, homogeneous or non-homogeneous. Right. So when the input is 0 or input is not 0. And we also covered a separable type of equation. And the third type is called homogeneous equation. So when the function can be written as homogeneous of degree 0. And then there's another one called exact differential equation. I presented, but I didn't give you the solution. And I said I will actually present a solution in the other course, 248. Okay. And this is the last type, Bernoulli type equation. So it's named after a mathematician called Bernoulli. The equation type looks like this. So this is what Bernoulli had worked on, okay, or he worked on this type of thing, and then they find a solution for this type of equation, roughly in the year 1695. Okay. So the idea of being a mathematician is you often try to conjure up a certain theory, and then you try to prove that theory, right? Yeah. And there are a lot of theory that actually proposed but not being solved. So this is one equation essentially he studied and he found a solution, right? And that's what we're going to look at today. How do we get this? First of all, as you notice, there is a y to the power of n at here. So n is not 0, then n is not 1 for Bernoulli to call it a Bernoulli equation. Because if you set n equal to 0, and this equation basically becomes what? If you set it to 0, so this term becomes 1, so this whole equation becomes a typical general first order linear ODE, right? And if you set this term to be 1, then you have y here, you have y in here, and then you move over here, so you get a homogeneous also first order, right? So there's no special about that. It's when n is not this, and then that's the special part. Okay. Because when n is not 0, not 1, it could be negative, it could be positive, right? Then this whole equation is not a linear equation anymore. It's a nonlinear equation. And the reason we present this is because this Bernoulli guy, he found an exact solution. So that's actually often in time is a luxury. When you have a nonlinear equation, not necessarily you always have an exact solution. Exact solution basically means by some effort you actually can derive y equal to specifically something, right? That's called an exact solution. So that doesn't apply to all situations. A lot of time when you have a nonlinear equation and you cannot solve it with an exact solution, then your alternative is to solve it numerically, which is what you're learning, right? Yeah. So that's the point. When a nonlinear equation have an exact solution, that's why it's kind of special here. Okay. So we will look at the procedures of how to solve it. Okay. The procedure set here. It does involve a little bit a substitution in here, so I need your attention here to be focused on this substitution. Okay. Yeah. This is the original Bernoulli equation. So here is what we're going to do. Okay. First, we will divide this y to the power of n by both sides of this equation. So that will give us y prime over y to the power n plus px. So y over y to the power n, it's y to the power of what? N minus 1 now, right? And then equal to q of x. So if you divide y to the power of n, okay, nothing changed, right? Just the format changed, and you get this new it's still Bernoulli equation. Okay. So in this format. Okay. And now we're going to do a substitution now. We will define a new variable u to be 1 over y to the power of n minus 1. So this term here is defined as u. Okay. That's introducing a new variable u, okay, to be this term, or y to the power of 1 minus n. Okay, so far so good. So from here we will take derivative of both sides of this equation here. Okay, so take a derivative u prime. Okay, and then y to the power of 1 minus n prime. It's a normal derivative. Okay, very normal derivative. So the derivative for this term is back to y. So you get 1 minus n. And then up there, 1 minus n minus 1, which is negative n. And then times whatever the function y is. Okay, y prime. So that's the derivative of this term. And it's equivalent to write it as 1. I'll write it on the numerator here. So this is y to the power of n. So 1 minus n over y to the power of n times y prime. Okay. And one more step, 1 minus n times y prime over y to the power of n. So I'm putting these two together. Okay, so basically nothing really, I didn't do anything at all, just putting these two as a fraction. Okay. The reason we're doing this is because here you have y prime over y to the power of n, and that's actually exactly what this first term added here. Okay. That's exactly the first term. So I'm going to replace this term because we already defined the u over here, right? Define a u. So I can replace this term as a u. So now I can actually replace this term using the relationship I find over here. Okay. So what's the relationship here? So y prime over y to the power of n equal 1 over 1 minus n u prime. So we can replace this y prime over y to the power of n with this 1 over 1 minus n times u prime. Okay. So now I have the original Bernoulli becomes the following differential equation, all in terms of u now. So the first one is 1 over 1 minus n u prime. This is the first term. The second term is px times u. And the other side is a qx. So after this, as you can see, that to the power of n term is gone, right? There's no such power n term anymore. And this has become a very typical first order linear differential equation now. I can multiply, yes?
How did you go from 1 minus n to 1 over 1 minus n?
How do I go from 1 minus n? Which part? This part?
Where you circle is 1 from there, 1 minus n.
Here?
How did you go from that to 1 over 1?
So which step? This step?
Yeah, and then to the next step.
To this step?
Yeah.
Okay. So I divide this 1 minus n to this side here.
Oh, okay.
Yeah. Right. So then you have 1 over 1 minus n times u prime. Yeah. Good? If this is still not clear, you can multiply this 1 minus n and get rid of the coefficient here and move it to somewhere else. Okay, and then you get this one here. So now you have, this is basically, depends on the n value, right? You have a typical first order. This is a first order linear ODE. Okay? Yeah. So from here, what type of approach or technique we can use to solve this one? What approach can we use? Integrating factor, which is just used in the midterm, right? So you can use integrating factor to solve it now. Okay. So the key, of course, right? Once you solve the u, and then you can solve for y based on your definition of u. Okay? So the key is essentially from here to here. Okay? Yeah. So I'll give you an example, okay, to take a look at the actual way of solving this. Now, what are the actual applications of Bernoulli equation? Okay, here's one example of application. So suppose you fire a bullet. Try to hit certain object, and the bullet will travel with the speed of v. Okay. So, study has shown that there will be resistance force for the bullet, and the resistance force of the bullet can be written as this expression here. So lambda 1v plus lambda 2v squared. Apparently, the higher the speed, and then the higher the resistance force is, right? Yeah, and it's nonlinear. Okay. And because of this resistance force, if I apply the Newton's second law to the bullets at here, so Newton's second law says m x double dot equal to the total force, right, applied to the bullet. So let's consider only the horizontal one. Then mx double dot is equivalent to, say, this is m dv over dt, right? So it's a dA over dt, it's a ma, and the acceleration is dv over dt, so it's m times dv over dt for mx double dot. And f is this term at here. So now if I move this around a little bit, right, and you can see and that's exactly in the format of the Bernoulli equation. And this here, the n value equal to 2. Okay, so that's an example of where you could use a Bernoulli equation. So you could solve this to get the solution for velocity, right? And roughly you can estimate how far it can go, right? Okay, so let's take a look at an example. Okay. So this is a very simple example. Not necessarily you have to use Bernoulli sometimes, but this one, let's write it down here. Y prime equal to AY minus BY squared. A and B are constant. Okay, they're constants here. And we want to solve for the y. Okay, so but when you look at this example here, if we never learned Bernoulli equation, but if you look at this example, you could still solve it, right? You can use what technique to solve it? Separating variable. Okay, so you can solve it. But if you write it, okay, like this, okay, and that's actually in the format of the Bernoulli equation. And here, right, this is a Bernoulli equation. The n equal to 2. Okay. So let's use this Bernoulli equation to solve the technique to solve it, and you can compare to a very typical separating variable. Okay. As a matter of fact, in this case, separating variable would be much easier than the Bernoulli's equations. Okay, yeah, because a and b are constant. So let u equal to y to the power of 1 minus n. Right, that's the steps, okay, from the Bernoulli equation. I think I repeated it many times when in this class. Okay, so a lot of the time I will encourage you to memorize formula, but another often in time I will not encourage you to try to memorize formula. I try to encourage you to go through the process, okay, instead of just rigidly memorizing a certain formula. Okay, because I know often in time when you memorize the formula, it might not actually does you good. Because I was saying that in the midterm, a lot of students when they calculate distance, they write down the formula, and without completely understanding the formula, and when they do the calculation, they got it wrong, right? So, but if you memorize, if you understand the procedure, it's not a difficult procedure, then you actually don't need the formula, right? Okay. So this is the case. I would encourage you to go through the process for each one here instead of just memorizing the final results. Okay. So n equal to 2. So plugging n at here equal to 2. So that's your u is y to the power of a negative 1. And then we take derivative of this both sides of the equation. So u prime and becomes negative 1 times y to negative 2, and then times y prime. Solving for y prime, and we get y prime equal to negative u prime over y to the power negative 2. Sorry, yeah, is that right? Pardon me? Divide y to the power negative 2, right? Yeah. Yes, yes. You simplify, it becomes y to the power of a 2, right? Yeah. When looking at my lecture notes here, it seems to be yeah, that's right. So this one can be u prime y to the power of 2. Okay. Okay. So y prime equal to u prime and then y squared. Right, that's the idea where we'll try to replace the y prime there. Okay. Okay. Oh, actually, you know what? Wait a second here. I missed a step myself. Okay. Okay, I'll do this. Okay, sorry, you can't do this, but I'll do this. Yeah. I missed one step. Before we do, what do we do again? We need to divide y squared, right, by both sides at here. Okay. So if I divide this, what do I get? I get y prime over y squared minus a 1 over y equal to negative b. Okay, that's the first step we should do. Okay. And now you let u equal to this and you take a derivative, then you get basically these whole terms here, right? Okay. So now I'm gonna replace, because my u is 1 over y. Okay, this is basically 1 over y. And then y prime over y squared. So y prime over y squared at here is actually negative u prime. Okay. So if you look at this one here, so this is y prime over y squared. Okay, is negative u prime. So I'll be able to replace both of these two terms with the new definition of variable u. Okay, so the new Bernoulli equation becomes negative u prime minus a times u equal to negative b. So this is the original differential equation becomes this expression. Okay, that's a very simple expression. Negative, 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 get rid of all of them. So u prime plus au equal to b. So again, from here you have really multiple approaches to solve, right? One approach, typical approach, is integrating factor method, but because a and b are constant, you can also use a separating variable technique. Okay, so I will use the integrating factor method just to go through the process. Okay, with all of you. Using the integrating factor method, you multiply sigma on both sides of the equation, okay. And then you want to find the sigma such that you can write the left side to be sigma u bracket prime. Okay. And in order to do that, your sigma needs to be equal to sigma times a. So sigma prime equal to sigma times a. The solution of that will enable you to do that. And that's d sigma over sigma equal to a times dt. Suppose the independent variable is t at here. So you get the ln sigma equal to at. So integrate both sides now. Right? You get ln sigma equal to at. So sigma equal to e to the power of at. Okay. Once you get the sigma, then we plug it back into our equation. The left side essentially is e to the power at times u prime, and the other side is e to the power at times b. Okay, and then the prime at here is d over dt, right? So you can move the dt to the right side, and then you can integrate both sides of this equation. So you get e to the power of at times u, And this integration at here is exponential one. That's pretty straightforward. So b over a e to the power of at plus a constant c. So then you can solve for u, and that gives you b over a plus c times e to the power of negative at. Okay. Once you get the u, because u equal to y to the negative 1, that's our definition of u. So plug it back, the actual u and that's your y. So overall your y equal to 1 over this whole chunk, right? Now you can simplify or not, that doesn't matter here, but you can always simplify a little bit. You can a moving down here, so a times constant c. Okay. If you have the initial value given, you can plug in the initial value, solving for the constant c. Okay. So that's the process. Okay. Using this example, if you have a Bernoulli equation, right? The second part of the process is nothing new. It's just the first part, how to arrive at this typical first order linear ODE. Right? So you just have to let the u equal to y1 minus n, and there are a few simple steps, couple simple steps here, okay, to enable you to rewrite your original differential equation into a typical first order linear ODE. Okay. Any questions on the Bernoulli here? Okay, so this could be anything that after midterm will be possibly covered in the final exam, but final exam will not cumulative. I mean, not cumulative means we will not have a dedicated example, for example, on system property. We may actually retest the convolution in the final exam. Okay, that because convolution is a very important concept. Okay. But anything that we learned after midterm, okay, will be part of the final exam content. Okay. All right. So any questions so far? So can move on to the next lot topic now. Complex numbers. The logical flow, okay, the logical flow of the topic, okay, will be, once we finish cover first order differential equation, as you can logically imagine what's next. Next should be what? Second order differential equation, right? Yeah. But in order to do that, to solve second order differential equation, we will make use of a new concept called complex number. Okay. First of all, have you learned complex number? Okay, so there are a few. Yeah, maybe you learned in high school. Okay, that's fine. You may actually learn this in the different courses. Okay, so this is one course, and then I believe in some electrical courses you probably also see that again. Okay. But anyway, so let's introduce what complex number is. Okay. First, let's take a look at the definition first. Okay. So in this class, as also in many of the textbook, we use small variable z. Okay, so small letter variable z to represent the complex number. And we write the complex number in this format. So z equal to a times j times b, or in some textbook we write a times I times b. So in my writing, as you probably see, really depends on my mood. I sometimes write this, sometimes write that, so don't be confused. Okay, and you can write either one of these, that's fine with me. Okay. So bottom line is, this is a complex number at here. Okay. This complex number it's not just like a regular number. Why is it called a complex number? Because over here, so z is equal to a real number. Okay. The a here is a real number. And then plus the imaginary part. So the second part, the JB, okay, we can call it basically imaginary parts. Well, more precisely, let's call it the B part. Okay, so the B here is imaginary part. The A here is a real number, the real part. So that's a difference, because it's imaginary. So it's not, you tell people 1, 2, 3, right? Those are real numbers. But complex number is not a real number. Okay, when people first propose a complex number, okay, it's actually useless. Yes. The G is called imaginary unit. Yeah, very good question. So the G at here, or I, is called an imaginary unit. Exactly, precisely, the G or I is equal to square root -1. Okay. Now this is where actually initially it received tremendous amount of resistance, right, from human beings, because we don't accept this, right? How could you have a -1 under square roots? Okay, that doesn't make any sense. When anything doesn't make sense, we don't accept it, right? So that's why this initially nobody would think this is actually useful. It's useless. Why do you use this, right? Yeah. But somehow it proved to be very useful in many areas. Okay, so sometimes seemingly useless stuff can be very useful, right? Okay. That's philosophy. Okay, so let's continue from here. Now you know what the complex number is now. Okay, let's understand a little bit more about the complex number. Okay. So just like a real number, when you have a real number, you put down, this is here a 1, 2, 3. Right, so that's a real number. You can put it down on an axis. And for imaginary number, we have similarly we have the so-called a complex plane. Okay, so we have a complex plane, and complex plane, very much like xy coordinates, you have two axes. One axis is called the real part, and the vertical axis called imaginary part. So basically, the A at here, right? The A at here, we sometimes call it the real part of the Z. Okay. And the B at here, we call that it's the imaginary part of the Z. Okay, so the A, B, okay, the real part of the Z, and imaginary parts of the Z. So the complex plane has a real axis and imaginary axis, and these two axes form a complex plane. Okay. If it makes it easier, you think of it as the XY plane. Okay. Then you can find, based on the actual A and the B value, if this is A and this is B, then you can find the corresponding imaginary, the complex number Z. Just like plotting coordinates x, y in the xy plane. So you're plotting this imaginary number in a complex plane. And this complex is sometimes also called an Argand diagram. So, but that's fine. Okay, you can think of this basically modified Cartesian plane here. And I sometimes also think of this. Even you can think of this as a vector. This is essentially like a drawing vector here, right? But it's not a vector. Okay, yeah. So we'll come back to this a little bit again. Okay. But more important, what we want to learn is we want to learn operations of complex number. Okay. So operation means how do we multiply, how do we add, and many other things. Okay, yeah. Some of the operations are very, very straightforward. For example, additions or subtractions. So let's say you have a two complex number, Z1 and Z2. Okay. If you're going to add or subtract the two complex number, then let's just add first. You just have to add the real parts and the real part together, and then imaginary part together. Okay? Yeah. So a little bit different from adding real number. And in real number, 3 plus 3, that's it. But this time involving two parts. One is real part and the other one is imaginary part. Another important which is dedicated to the imaginary is called conjugate. Okay. The term is called conjugate of a complex number. Conjugate. So what does conjugate means basically is this. Let's say we let z equal to a plus jb. Okay, it's a complex number. Okay. Then more precisely, let's call it the complex conjugate. So the complex conjugate of z, okay, is, okay, so we use z star to represent the conjugate operation. Some textbook use, there's a hat, there is a bar on the top of the z, okay, to indicate the conjugate. So I'm going to use z star, okay, in this class, okay, to represent the conjugate operation. So then what happens is, if this is your original complex number, then when you put a star at it here, which means you want to calculate the conjugate, all you need to do is to change the positive JB to negative JB. Okay, so that's called conjugate. From graphical point of view, if this is your original a plus JB, then the conjugate action on this complex number will yield a new complex number which become the red one, right? Because b becomes negative b. So essentially, the conjugate is a mirror of the original complex number, right? Okay. So let me ask a simple question. What is the conjugate of a real number 3? It's 3. So that's why you have this complex conjugate, right? So if it's a conjugate of a real number, not a complex number, then you're not changing anything, right? Yeah. Okay. Now, there are some operations involving both the original complex number and its conjugate will actually oftentimes make things easier. So, for example, if I If I add the original complex number and its conjugate together, what do I get? Exactly, you just get the real part. So that's actually a very good application, as later we'll make use of this simple property. If I want the real part of this original complex number, if you're given this, for example, I have a complex number z. I want to extract the real part out. So what do? We just have to add the z and the conjugate and divide it by 2. Then you get the real part of that complex number. Okay. So similarly, if you subtract the conjugate using the original minus its conjugate, and we're going to end up with 2g times b. 2g times b. So that basically means I could extract the imaginary parts of this complex number by doing this operation. Okay? Yeah. So those two very simple, very simple property, but we actually will use that to prove a few other things. Okay, that's addition, right? And that's conjugate. And the next one, so 1, 2, 3, multiplication. So multiplication. So let's use two complex numbers to illustrate. Z1, Z2 are the two complex numbers, A1, B1, A2, B2. Now we multiply the two complex numbers Z1 and Z2. So this time you have very much like a multiplication of real numbers. Okay, so you're going to multiply things together, but you have to keep in mind of the difference now. So when you have two terms multiply each other, and you naturally will multiply into each bracket and expand them out, right? Yeah. So what do we do? Let's see, A1 multiplied by A2, and then A1 multiplied by B2. Okay, and then you have the J in the front. And then you have a JB1 times A2. So this term times A2. And then you have JB1 times JB2. So that's J squared B1 B2. It's very much like expanding a multiplication of two terms, like x plus y times a times b, right? Yeah, the bracket a plus b. Okay. So nothing really special here, but you do need to make small adjustments. Okay. For the J squared. So if you recall that the definition of the complex number, right, in the definition, the J is called the imaginary unit, which is square root of square root of -1, right? So then J squared will become -1. Okay. So that's power square root still works, and still the same rule. Okay. So this time you can group the real together and imaginary together. So you get A1 A2 minus B1 B2 plus J A1 B2 plus B1 A2. Okay. So that's the results of this multiplication of two complex numbers. So I want to spend a little bit of time at here basically on the g squared, right? So what is g squared? G squared is g times g. That's what g squared is. So let's do this, okay? Let's do this. I'll do g times 1. Okay, let's understand the g a little bit here. G times 1. What's g times 1? It's g, right? Yeah. Okay, so graphically, let's see like this. Suppose you're initially at this 1 location, right? That's 1. Okay, that's real number 1. So when you multiply real number 1 with g, you get the g, right? So where is it? It's over here. Okay. So what happens is you started at here, and once you multiply the g, and you end up at this location. Okay? Yeah. So let's keep going. So what is g times g? So you basically multiply the g again with this results g at here, as we just learned, is equal to -1, right? So now, once you multiply this, where is it now? It's -1. Okay. So what about g times what? G times g cubed now, right? So g times g squared. So this is g squared here. Okay. So g times g squared. So technically speaking, so -1 times g, which is -g. And -g is where? It's here, -g. So we're here now. So what about g to the power 4? It's g times g cubed. So g times g cubed is g times -g, which is -g squared, and which is 1. So finally, okay, with these few steps, you come back to 1. Okay, come back to 1. So what did you notice? Every time when you multiply j, shift by 90 degrees. Exactly. This is actually in image process. When you multiply an image with, if you have an image at here, when you multiply this image with j, guess what happens? The whole thing will not shift, rotate by 90 degrees. Okay. Yeah. So that's a very simple manipulation there. Okay. Yeah. Okay. So only 2 minutes left, so I think I'll stop here, and we'll continue complex number next week.